When you run Monte Carlo experiments, you need to make a decision on how many iterations you must run in order to get results that make you comfortable. But it would be even better if AnyLogic itself could tell you how many iterations you need to run in order to get results that you can trust. And this is what we're going to do on this video. We'll automate this process. And in order to understand this, you need to understand confidence intervals, and we have a couple of videos around this topic, and you need to understand custom experiments as well. And we also have a video on this topic, and I will leave those in the description. AnyLogic is already supposed to have this feature. If you go to the Monte Carlo experiment in the properties, you will see the varying number of replications. And this is supposed to stop when the confidence level is reached. But this feature has never worked in AnyLogic, so what we're doing here is using a workaround with custom experiments. So what we're going to do on this video is first a reminder of confidence intervals, then we will automate the process to find the number of replications needed for your results to be trustworthy, and finally we'll add a bonus, which is how do you do a compare runs experiment using custom experiments. Okay, so let's get started.
So the aim of this Monte Carlo experiment is to run the model a certain number of times until reaching a certain confidence level. So what does that mean? This means that we need to search for the minimum amount of times that we need to repeat running our model until we reach a certain confidence level that the variable value that we are looking for is going to belong to a certain confidence interval. But at the same time, we don't want this confidence interval to be very wide. And this is why we will also specify a percent error, which is the percent variation around the mean. So for example, the result we get may be that we need at least 50 runs in order to be 95% confident that our value belongs anywhere between 5 and 7. So in order to design this experiment, we are going to need to calculate two formulas. The first one is the confidence interval, which is equals to the mean of the values that we get out of the certain amount of runs that we do, plus or minus a margin of error. And this margin of error is equals to a t-value times the standard deviation over radical sample size. The t-value is a value that we are going to get out of a table that depends on two factors, which are the chosen confidence level and the sample degrees of freedom, which is equal to sample size minus 1. So every time we run a new run of the model, our sample size is going to become bigger, and then according to that, we are going to calculate the new margin of error and the new confidence interval until we reach the acceptable error percent that we need with the confidence level that we have chosen. So let's see how this goes. So this is actually very similar in concept to the normal Monte Carlo simulation with the fixed number of runs, which means that we are going to use the same old for loop that we saw in the other custom experiments from the previous video in order to call for the function that runs the model from the custom experiment for a certain amount of times. However, the difference here is that we don't really know how many times we are going to run. And this is because this value is what we are actually looking for. So what we want to do is to make the for loop stop when the error percent we have indicated has been reached. So there are four values that we should provide in the Excel sheet for this experiment. The first value is the minimum replications, which is the minimum amount of time that the model should run. The maximum replications means the maximum amount of times that the experiment should try running the model. So if it reaches the needed confidence level with the needed error percent before the maximum replications are reached, then in that case, the experiment will just stop. But if it doesn't reach that value before the maximum replications, then it will just continue to run the model until it reaches the maximum replications. The third value is the confidence level. The last value is the error percent, which is the percentage of the mean that we want our value to vary. And since the t-value is not a constant value, but it will change based on the sample size and the confidence level chosen, what we did is that we entered this table in the Excel sheet, and this table is going to be used in the model in order to find the t-value. We also entered the z-value, so for the cases when the sample size becomes greater than 100, this means that we won't need to use the t-value anymore. In that case, we will need to use a z-value. The z-value is used for big sample size. So again, for more details about this issue, you can check the previous videos. So in the model, as we said, we are going to add everything related to the custom experiment in this simulation experiment window. So what we did regarding the t-value is that we entered each column of the table as a table function. So what this means is that we are going to give the degrees of freedom to this function, and this function is going to return the t-value, and we are going to choose the appropriate function that we are going to use based on the confidence level that is entered in the Excel sheet here. Also added a statistics element. This is the element where the value of our variable will be stored after each run. So this means that this statistics elements will contain our sample. And this way we can easily calculate everything we need, like the average and the standard deviation, using the built-in functions related to this statistics element. So if we go to the Start Experiment button, you will see here that with every iteration in our for loop, the t-value is going to be calculated based on the sample size. So statistics count is the sample size minus 1 gives us the degrees of freedom, and so the t-value is going to be calculated accordingly. For the cases when the sample size is greater than 101, or in other words, when the degrees of freedom is greater than 100, as we said, we are going to use in that case the z-value instead of the t-value, which is also going to be chosen from this set based on the confidence level. So the arguments that we are going to provide to the function are first the seed. So we just send any value between 1 and 1000 as the seed. And we are going also to send the statistics element, since this is the element that is going to be used to do all the calculations of the formulas. And we will send also the t-value that we have calculated here, and the error percent and the minimum reps that are chosen in the Excel sheet. And these other elements, I'm going to talk about them later. These are related to the charts that we are going to add. And then here, inside the custom experiment function, the first part is going to be the same as in the parameter variation experiment from the video previously posted. But then, after each run, the value of the variable that we are looking for is going to be stored in the statistics value. So in our case, the value is going to be this variable, which is the number left, which is the number of agents that leave the system without being serviced. So this value is going to be added to the statistics element, and based on that, after each run, the needed calculations are going to be done. So the average of the sample is going to be calculated, the standard deviation, and finally the margin of error. And based on the margin of error, the percent of mean, which is the error percent, will be calculated, which is simply the margin of error over the average. Now, if the percent of mean that is calculated here is less than or equal to the acceptable percent error that we have indicated in the Excel sheet, which is this one, then in that case, the experiment is going to stop. How will this happen? Well, we have indicated that our function will give a return value. This value is a Boolean value. So this value, which we are calling stop, is false at the beginning. Once the percent of mean has reached a value which is less than or equal to the acceptable percent error, then this stop will become true. The function will return at the end the value of this stop variable. And as you can see here, when this return value is true, the for loop will break, which means that the for loop will stop continuing its iterations and will just stop at the current iteration that it has reached. So this is the main idea. This is the main difference between this experiment and the other Monte Carlo experiment with a fixed number of runs. So when we reach the error percent that we need, the function is going to return a true value to this for loop. And based on that, the for loop is going to stop its iterations. And this means that we will know based on that the number of runs that we needed in order to reach the needed confidence level with the needed error percent. Now, in order to see the results of our experiment clearly and in a more visual way, we have added these four graphs. So, for example, this graph is going to show us the error percent of each run. The error percent is going to be stored in this data set, and this is why we are going to give this data set as an argument to the function in the custom experiment. And here in this function, after each run, the needed values are going to be stored in this data set. And finally, these amounts or these values are going to appear in this graph. And in a similar way, here we are showing the value of the variable we are looking for in each run using a histogram. This graph, on the other hand, shows how the lower bound and the upper bound and the mean of the confidence interval will vary with each run. And finally, this chart will show us a simple representation of the final confidence interval that we have reached. So it will show three bars, one for the lower bound, one for the upper bound, and one for the mean. So let's run our experiment to see the results. So here we have indicated a minimum replications of 2, a maximum of 500, a confidence level of 0.95 or 95%, and an error percent equals to 0.05 or 5%. So I will start my experiment. Okay, so as you can see at the end, these are the results we got. So this graph will show us how the error percent has varied until it reached the needed value we indicated in the Excel sheet. This shows our needed variable in histogram form. And this graph, as you can see, this color will show the lower bound, how it is varying, then the upper bound, and this is the mean using this color. So we have around 380 iterations. So this is the number of runs that we need in order to reach the indicated error percent. As you can see here, the three values are very close to each other because our confidence interval is only varying 5% around the mean. And as you can see here, we can see clearly our final confidence interval, which ranges from a lower bound of 15.15 to an upper bound of 16.74, and the mean is equal to 15.95. And finally, the last experiment that I want to show you is the compare runs. The compare runs is actually very similar to the parameter variation experiment because each run, a certain parameter is going to have a certain value. But the difference here is that instead of this value having to be calculated based on the step that we provide, here we are simply going to provide all the values for the parameter that we need to compare. So this means that in our for loop, every run is going to use one of these values for that parameter to do the run. Now, this experiment is sometimes used to see how the value of a certain variable that varies a long time changes with the change of that certain parameter. So this means that we will need to monitor how the value of this variable is changing with time. But this is not possible using the function we are doing in the custom experiment. And this is simply because what this function is capable of doing is giving us a result at the end of the simulation run, rather than seeing how a certain value will vary with time. And this is why, in order to be able to do that, we will need to add a certain data set in our upper level agent, and this data set is going to store the value that we are looking for and how it changes with time. So for example, if we need to know the size of the queue and how it varies a long time in this service plot, we can add a data set that stores the service queue size a long time. And in that case, what we do in the custom experiment is that at the end of the run is simply to add this data item to a chart that we add in our simulation experiment window. So by adding this data set in our upper level agent, we are giving our custom experiment the access to this data set because our custom experiment can access the upper level agent. And this is why at the end, the custom experiment will be able to add the contents of this data set to one of the charts that we have here. So this chart is going to show us how the queue size will vary a long time in each run, and this is something we have already done before. This one is going to show us the value of the number left variable with each run. So let's run the experiment. Okay, so the experiment will run for the number of times based on the number of values that we entered in the Excel sheet. So as you can see here, we are able to see the value that we are using for the parameter, as well as the value for the variable number left that we get out of the run. So this will just show us the value in each run. And this graph, on the other hand, will show us how the queue size is varying with time. That's why you can see 6 plots, each relevant to a value of the parameter. So all these examples that we have shown show the amount of flexibility you can get when you use custom experiments. So the next time you want to do something that doesn't exist already in any logic, you can simply use custom experiments to do whatever you want.